Good morning. This is lecture number 91 in the ABCs of Communism series that accompanies volume 6 when it appears. And this will be chapter 87 in that volume 6, which is on communism in Arabia and Africa. This is going to be the first chapter in volume 6. But it's the last lecture in the accompanying YouTube ABCs of Communism series, because I wanted to wait until we had more results of this year's field work in Africa in my hands, wait as long as possible before giving the most recent picture of human origins to you. And before we move on to that, a few comments are in order. What has been new in Marxist archaeology is my identification of the cause of the socio-cultural evolution of Homo, and that it was the learning how to use culture to, one, secure command of the African environments while avoiding surplus social product creation. The multi-million-year pattern of African Dryopithecine evolution served to increase these man-like apes' cubic centimeter cranial capacity as preparation for learning to use culture to buffer the natural world and secure mastery over it. And two, that this surplus product avoidance was also the cause for Homo's subsequent migration across the Old World. Now, this migration of Homo throughout the Old World was also caused by their need to refrain from making too much social product. Mastery of their universe via culture implied surplus. On the other hand, daily surplus social products on hand could create envy, jealousy, and coveting. These are the things that lead to social disillusion. Dialectically, the converse is that it is the social unity of cooperating creatures that gives Homo its natural survival edge. In short, being able to understand that preventing the creation of too much social product was dangerous to unity was also the reason for the original Homo migration out of Africa. People migrated in order to encounter new environs that were more challenging. In the new Eurasian environments, yesterday's surplus was today's necessity. I have been proving this original proposal in the preceding volumes. Now we are moving backward in time and space from Arabia to northern Africa, and then to the rest of Africa. And we are moving backward in the biological sociocultural evolution of our pre-Homo ancestry to uncover the origins of Homo as a genus. The fossil evidence for the evolution of human-like apes to ape-like humans requires a clear understanding of this early fossil primate evidence. And our object in this chapter is to gain a deeper understanding of how culture, by which I mean technology, social organization, and ideology, came to be the primary driver in the biological evolution of Homo. What scientists have been working on for decades is clarifying the detailed possibilities on the fossil Dryopithecine and offspring evidence in Europe and Asia. Now, why is this important to us? Because we needed to eliminate the European and/or Asian fossil ape evidence from the gene pool that gave rise to Homo australopithecus in Africa. Alternatively, to explain how the European and Asian fossil ape evidence fit into the line leading to Homo australopithecus. In conclusion, I'm going to give you the results of today. We know that the European and Asian Dryopithecines led to dead ends, and only those in Africa led to Homo australopithecus. This evidence has been coming in since I started volume 6 and the accompanying lectures that preceded this one. Now, as to the fossil evidence, you'll recall that the Egyptopithecus, the ancestral monkey primate that lived during the Oligocene, gave rise to man-like hominoids and Old World monkeys. By the early Miocene, there were a variety of these man-like apes with different sizes and diets. Now, Proconsul had monkey-like locomotion and ape-like jaws and teeth. Mourotopithecus exhibits the locomotor pattern of the later great apes while retaining dental anatomy distinct from those later great ape fossils. By 13 million years ago, there are fossil apes in Europe and Asia belonging to a group that include living great apes and humans. Some of this group had locomotion of the form found in chimpanzees and orangutans. All these apes matured slowly, like the living apes, and had brains of the same size as chimpanzees. During the early Miocene, they came to inhabit most of the tropical and subtropical forests that covered large parts of the Old World. Our ancestral apes exploited these forested environments in Africa, Southwest and South Asia, and East Asia. They also spread into parts of Europe. Fossils representing many Miocene ape lineages include the common ancestors of orangutans, chimpanzees, gorillas, and humans. They existed in the late Miocene between 15 and 6 million years ago. Most of the rest of the ape lines of the Miocene became extinct. Now we should note 3 ape lines. One, the first, is those that invaded South Asia and its descendants that colonized the tropics of China, Southeast Asia, and Indonesia. Asia has produced many great ape fossils from the Miocene up through the Pleistocene. These fossil apes are distinct from those found in Europe and Africa, and they had no direct relationship to the hominids. Their most recent members are the living and fossil orangutans of the genus Pongo. Today, orangutans survive as remnant populations only on the islands of Sumatra and Borneo, though fossil Pongo is found as far north as China. From China in the east to Turkey in the west, the fossil apes of Asia were a large and diverse group. Secondly, the other lineage that arose in Africa and spread across Europe, diversifying into several species of the single genus we call Dryopithecus. For example, it gave rise to the Oranopithecus, Gryptopithecus, and Hispanopithecus. These European apes share many features with the living chimpanzees and gorillas, and are the closest fossil relatives of the living African apes and humans. And thirdly, however, our own lineage of man-like ape hominoids arose at the end of the Miocene in Africa and stayed there. In other words, the common ancestors of humans, chimpanzees, and gorillas belong to a separate group from both European and Asian fossil apes. Our earliest ape ancestors was a Dryopithecus, and very much like the early Dryopithecines known from European sites. We know now that the critical period of 10 to 7 million years ago saw African Dryopithecines evolving on a separate path from its Asian and European relatives, and this is when the African apes and hominoids diverged. The line leading to Homo australopithecus is just now being clearly identified. The anatomy of these ancient apes is the starting point from which our contemporary study of human evolution begins. Now I want to take a closer look at the fossil ape genera. The living great apes are the relics of times long since past. As we have seen, their ancestors originated in Africa at the Oligocene-Miocene boundary time. By the beginning of the Middle Miocene, they had expanded their range into Eurasia. Field investigators now provide an updated chronology that incorporates recently discovered Iberian taxa and that allows the re-evaluation of the age of many previously known sites based on biostratigraphy and magnetostratigraphy. These results show that identifiable Eurasian Chenopithecines, specifically Gryptopithecus and Chenopithecus, are much younger than previously thought. Now they date 14 million years instead of 16 million years ago. The Eurasian Pongines and African hominoids may have independently evolved in their respective continents from similar Chenopithecine ancestors. An early Middle Miocene intercontinental range extension, followed by the geographical separation of a population by physical barriers, such as those presented by the Mediterranean, gave two closely related species. The European Dryopithecines may have given rise to the Pongines rather than hominoids. Now, current evidence indicates that hominoids originated in Africa, where they experienced an expressive early radiation during the early Miocene. During the Middle and Late Miocene, hominoids from Eurasia recorded by a plethora of new forms at the same time as there was a decline in hominoid diversity in Africa. Geographic isolation played a significant role, in the creation of these new species. Here we provide an updated chronology for the Miocene hominoid sites of Europe, Turkey, and Georgia, which incorporates Iberian sites where several new hominoid taxa have recently been described. Now, for the oldest Eurasian hominoid, a partial upper third molar from Engelsweiss in the Bavarian Molasse Basin, previously tentatively attributed to Gryptopithecus, has been considered the oldest Eurasian hominoid. An age of 17 million years was favored for Engelsweiss based on associated mammals and lithostratigraphic correlation with the main units of the Bavarian Molasse confirmed previous age estimates. However, summarizing new data on the exact stratigraphic provenience of the hominoid teeth, hominoids dispersed into Eurasia by the latest early Miocene. This earliest occurrence predates the other oldest Eurasian sites by at least 1.3 to 1.5 million years ago. Even more surprising is that hominoids have not been recorded from Sandalshausen, a temporary equivalent locality from the Bavarian Molasse that after decades of excavation has delivered more than 50,000 identifiable specimens. Now, for the middle Miocene sites, after Engelsweiss, the oldest hominoid sites of western Eurasia are Passalar and Kandir in Turkey. Both record Gryptopithecus alpani, and recently a second hominoid, Keniapithecus kizili, reported from Passalar. On biostratigraphic grounds, Kandir can be correlated to either mammal Neogene zone 5 or 6. Unfortunately, magnetostratigraphic results do not allow an unambiguous correlation. 3 correlations are possible, and although the latter correlation requires assuming large sedimentary and or tectonic hiatuses in the Kandir region, based on biostratigraphy, Kandir was initially correlated to one and subsequently to another. The presence of the large fossil rodent Megachrysotodon colongensis argues against the former correlation. However, an alternative correlation is supported by the rest of the fauna, resulting in an estimated age of about 13.4 to 14.1 million years ago. Regarding Pansalar, the correlation must entirely rely on biostratigraphy, and the rodent fauna suggests a correlation to the equivalent Turkish zone F. Therefore, as further suggested by the macrofauna, Passalar would be close in age to Kandir, although slightly older. A hominoid tooth from the lower synapse member in Turkey might be somewhat older. Based on the associated fauna, this find has been correlated to the locality of Inonu, with an estimated range of about 15 million years ago. Nevertheless, this earliest occurrence is much younger than customarily assumed and post-dates by at least 1.3 million years the earliest Eurasian occurrence of hominoids as documented by the Engelsweiss finds. The hominoid sites from Divinska Nova Ves in Slovakia and Klein Hadersdorf in Austria include several teeth and postcranial bones attributed to Gryptopithecus swissi. These localities occur in transitional facies that delivered a mixed assemblage of terrestrial vertebrates. Plankton fossils from the same facies suggest an age not older than 11.6 million years. The clay pit of St. Stephan im Lavental in Austria, that is the type site of one Dryopithecus species, correlates with rodent data, and that data, along with the mollusk fauna from this site, indicates a late Sarmatian age of 7 to 8 million years ago. In Catalonia, the densest middle Miocene hominoid record occurs at the Valles Penedès Basin. Their field results from the 250-meter thick local stratigraphic series recently led to the description of 2 new ape genera and species and some fragmentary hominoid remains yet to be described. High-resolution magnetostratigraphic studies allow an estimated age of about 12.2 to 12.3 million years ago, whereas the youngest occurrence is a single tooth from Can Mata 1 dating 11.2 to 11.1 million years ago. The remaining hominoid sites cluster at a tight interval of less than 200,000 years, from 11.8 to 11.9 million years ago. Cevapithecus occidentalis has an uncertain stratigraphic provenience, but an estimated age of 12.5 to 11.4 million years ago. Hominoid sites from Castel de Barbera and Sant Quirze correspond to the Demacrochrysotodon crucifonti and Megachrysotodon thyricus concurrent range zone, and would be somewhat younger than most of the other hominoid sites. This local biozonation is also seen in France, and this allows specifying the age of some ancient localities there, including the fissure fillings from La Grève Saint-Alban. Dryopithecus fontani has been reported from La Grève fissures M and L3. La Grève M is correlated to the Valles Penedès Dryopithecus lartete and Megachrysotodon ibericus concurrent range zone, and the 12.4 to 11.8 million years ago date, whereas La Grève L3 and L5 sites are correlated to the Dryopithecus crucifonti plus the Megachrysotodon ibericus concurrent range zone of 11.8 to 11.2 million years ago. Now finally, the karstic site of St. Gaudens, a type site of Dryopithecus fontani, has a poor large mammal assemblage that nevertheless suggests a date of about 12.5 to 11.1 million years ago. And that brings us to the late Miocene sites. During the early Vallacean, that is the earliest late Miocene, hominoids are still diverse and widespread across western Eurasia. In the Iberian Peninsula, most hominoid fossils occur in the Valles Penedès basin, where they are represented by Hispanopithecus latalis and Hispanopithecus crucifonti. This genus occurs at several early Vallacean sites, including Canponsic, Canyobateris I, and becomes rarer during the late Vallacean, being last recorded at La Tarumba I. The range of Hispanopithecus in the Valles Penedès basin is between 11.1 and 9.5 million years ago, according to the detailed bio and magnetostratigraphic data available for most of the sites. Regarding the mandible of Hispanopithecus crucifonti from Telluria del Ferrol in the small intra-Pyrenean Suda-Urgell basin, detailed information is not yet available. This locality delivered a large mammal assemblage that included Hippotherium primigenium and indicating a Vallacean age. The location of this site in the lithostratigraphic unit of Belstar enables further refinement of this age because of two small mammal sites from the same unit. These localities can be correlated to the Chrysotodon Hartenbergeri local range zone of the Valles Penedès, indicating an age close to that of Canbontic of 10.4 to 9.9 million years ago, which is the type locality of Hippotherium crucifonti. In Germany, isolated hominoid molars have been recovered from a series of fissure fillings from Wisberg and Eppelsheim. These sites are located within the well-known Dino-Therinsand Formation, which ranges from the early Vallacean to the early Taurulian. The fauna associated with the fossil apes from Eppelsheim is of an early Vallacean age. The fauna from Wisberg is mainly Vallacean, with Astarachian and Tyrolean specimens. The few faunas from karstic Salmendingen include the Vallacean beaver Dipoides, which dispersed into Europe from North America during the early Tyrolean and is frequent in karstic sites. The same situation occurs at Melchingen with Vallacean and Tyrolean elements, including the beaver Dipoides. The remaining German karstic sites, Ebingen and Trachtelfingen, have not produced datable material for the few primate teeth. In Austria, the Vienna Basin chronology of Götzendorf and Mariathal is firm enough, given the fluvial and lacustrine sediments related to Lake Pannon, where a highly detailed biostratigraphy based on molluscan faunas is available. Götzendorf can be correlated to the late Pannonian zone F2, that is terminal early Vallacean. Mariathal is correlated to the early to middle Pannonian age, indicating a slightly older Bayesian age, and all these finds are very fragmentary and contrast with a much more complete material recovered from Rudabanya in Hungary, attributed to Hispanopithecus hungaricus. This site, located within lacustre sediments of Lake Pannon, has a rich faunal assemblage that, along with the Hypotherium primigenium, suggests an age of about 10 to 9.8 million years ago, closer to the early-late Bayesian boundary. During the Bayesian, two additional distinct hominoid genera are recorded in the eastern Mediterranean: Ankaropithecus in Turkey and Oranopithecus in Greece. The former is known from the densely sampled synapse formation, and its age is well documented at about 9.9 to 9.7 million years ago. Therefore, the age of the specimens would lie close to the early-late Bayesian boundary, being very close in time, if not synchronous, to the specimens of Coniobateris at 9.7 million years ago and Rudabanya at 10.0 to 9.8 million years ago. Hominoids are last recorded from the Valles-Penedès Basin at 9.5 million years ago, whereas their youngest unambiguous record from Central Europe is that of Rudabanya, 10 to 9.8 million years ago. Nevertheless, they clearly persist longer in the eastern Mediterranean, so that many late Miocene hominoid sites of that area have been assigned to the Tyrolean. These latest hominoid occurrences comprise that of Grecopithecus freibergi from Pyros Vasilicis in Greece. The mammal fauna from this site is too fragmentary to reach sound chronological conclusions, although several taxa, and then I list them, indicate a Tyrolean age of 8.7 to 6.8 million years ago. A maxillary fragment attributed to Udamnopithecus garadziensis from the Chiraki Formation close to Udamno in Georgia has also been assigned to the Tyrolean. The Chiraki Formation is a 300-meter thick clay deposit with two mammal localities called Udamno 1 and 2. The primate remains were found 40 meters above Udamno 1, which yielded a rich mammal assemblage, including a late Bayesian age specimen. Udamno 1 yielded a date of 9 to 8.7 million years ago. Therefore, Udamnopithecus would be a late Bayesian taxon, roughly contemporaneous to Oranopithecus macedoniensis, although maybe slightly older. Furthermore, another species of Oranopithecus called Oranoturcae has been described from Korakir in Turkey, and this site delivered a rich assemblage including small and large mammals. The rodent fauna is dominated by the murid Hans de Bruhinia, exclusively known from this site, but further includes two species of Byzantia and a species of Pseudomyrionis. These elements suggest a correlation to the Turkish zones J or K, all of MN9, MN12, although a tentative correlation to MN11 of 8.7 to 7.9 million years ago has been favored. The macro-mammal fauna also suggests an MN11 age, although certain ruminants, and then I list them, would alternatively favor an MN12 age of 7.9 to 6.8 million years ago. On this basis, a somewhat younger age, MN12, cannot be discarded for O. turcae. Regarding the hominoid dental material from the Amatovska Formation in Bulgaria, although additional faunal data would be required, a Tyrolean age of 8.7 to 4.9 million years ago is suggested by the presence of Protragelaphus and Anancus. Finally, the latest West Eurasian hominoid is Oreopithecus, which evolved under insularity conditions in the Tusco-Sardinian Paleobioprovince during the late Miocene. The dating of the Oreopithecus-associated fauna has always been problematic because of their endemism. The Basanello-Sinigiano Basin succession from Tuscany has been divided into four different biochronological units, V0 to V3. Unlike V1 and V2, the V0 and V3 faunas are not completely endemic, and can be correlated to the MN11 and MN13 respectively. Therefore, the Australopithecus faunas were short-lived, spanning from 8.5 to 7.6 million years ago. This fully agrees with the radiometric dating of 7.5 plus or minus 0.03 million years ago for a volcanic layer within the Bacchanello deposits. Thus, Australopithecus was contemporary with other Tyrolean hominoids from the eastern Mediterranean, but may have survived until slightly later, probably becoming extinct when the Tusco-Sardinian archipelago became connected to the mainland about 7 million years ago. And for the conclusions about Europe, if the stratigraphic provenience of the Engelweis tooth is correctly recorded, hominoids must have first dispersed into Eurasia shortly before the Langian transgression, that is, before 16.3 million years ago. The partial molar from this locality, however, offers very limited morphologic information other than indicating an attribution to a thick enameled undetermined hominoid. The previous assignment of this tooth to Gryptopithecus was based on an old previous age estimate for the Turkish localities where this taxon had been securely recorded. Here we show that, on the contrary, these localities are much younger, about 14 million years ago, and this considerable temporal gap, therefore, casts serious doubts on the attribution of the Engelweis hominoid to Gryptopithecus, so that a phylogenetic link with Chenopithecines remains to be established. Thus, after the Langian transgression, a group of hominoids of African origin, the pronograde Chenopithecines must have extended their geographic range into Eurasia, first in Turkey, where we have both Gryptopithecus for Eurasia and Chenopithecus in Eurasia and Africa, and the retention of Chenopithecine features in the late Middle Miocene Iberian Dryopithecines at about 12 million years ago means that the Eurasian hominoid radiation might have originated from some Chenopithecine ancestor. It remains to be ascertained whether this radiation gave origin exclusively to extant pongines or to both pongines and hominoids. And this probably reflects a true regional extinction event, the so-called Bayesian crisis, resulting from the crossing of some paleo-environmental threshold that hominids were unable to manage. Only in the eastern Mediterranean did hominoids survive somewhat longer, that is, until from 8 to 7.5 million years ago, probably thanks to the pre-existing adaptations of the Australopithecines to the environmental conditions of the Greco-Iranian biome. Ultimately, however, the paleo-environmental changes associated with increased aridification and seasonality eliminated hominoids from western Eurasia during the Tyrolean, further leading to their progressive diversity decline and geographic range restriction in Asia throughout the Pleistocene. This heavily contrasts with the evolutionary response of hominoids to climatic change in Africa. There, coinciding with the extinction of European hominoids, there are purportedly bipedal hominoids recorded during the late Miocene, that is, dates of 7 to 6 million years ago, for the fossils Sahelanthropus and Auroran, and during the latest Miocene, that is 5.8 to 5.2 million years ago, and earliest Pliocene, 4.4 million years ago, for Ardipithecus. The elimination of the European and Asian Dryopithecines from consideration as the direct Dryopithecine ancestors of Homo australopithecus is a giant step forward. We can now focus on the diagnostic factors leading to language, culture, and year-round female sexual receptivity among the African Dryopithecines. So, going a closer look at the African Miocene Dryopithecines today. At the end of 2007, fossil hunters exploring the eastern edge of the Rift Valley of Kenya found the jawbone of a 10-million-year-old Dryopithecine ape. It is the closest relative of the common ancestor of humans, chimpanzees, and gorillas yet found. These ancestors of humans and chimpanzees split about 5 to 7 million years ago in the middle to late Miocene epoch. Now an international team of researchers are reporting the discovery of a new species of extinct ape in Kenya, making it the second large-bodied ape discovered recently in Africa from this critical time. Yutaka Kunamatsu, a paleoanthropologist at Kyoto University in Japan, and colleagues discovered the new species in Nakala, Kenya in 2005. The researchers recovered the partial lower jaw and 11 teeth of an ape dubbed Nakalapithecus nakayamai, which lived almost 10 million years ago. They reported that in the proceedings of the National Academy of Sciences, and they found the new species less than 30 kilometers or 18 miles from the Samburu Hills, where another large-bodied ape, Samburapithecus kiptalami, which lived 9.6 million years ago, was discovered a few years ago. The discovery of Nakalapithecus shows that there were two different large hominoids, even within a very narrow range of time and space, in the early late Miocene of Kenya, says Kunimatsu. Unlike S. kiptalami, which many researchers think was not on the heels of the discovery of comes hot on the heels of the discovery of another ape that lived at about the same time in Ethiopia, called Sauropithecus absithecus, whose teeth closely resemble those of modern gorillas, as reported in Science magazine last year. Now, taken together, these finds suggest that once apes originated in Africa at least 22 million years ago, they never left, although some did migrate to Europe and Asia, where they flourished. Now, this specimen forms yet more evidence that there was a flourishing and diverse population of apes in the late Miocene of Africa. One expert suggests that the gap in the fossil record for Miocene apes in Africa may have existed because few people have looked for apes in the right time and place in Africa, and because many of the apes lived in wooded habitats where the remains were less likely to fossilize in acidic soils. In 2017, last year, anthropologists found a complete cranium of a Miocene ape from Africa that lived in the hazy period before the human lineage split off from the common ancestors we share with chimpanzees some 7 million years ago. Now scientists in Kenya have found their prize at last, an almost perfectly preserved skull, roughly the size of a baseball. The catch? It is from an infant. That means that although it can give scientists an idea of what the common ancestor to all living apes and humans would have looked like, much reconstruction will yet be required. The discovery in Kenya of a remarkably complete fossil ape skull reveals what the common ancestor of all living apes and humans must have looked like. The find belongs to the infant we just mentioned, which lived about 13 million years ago. An international team led by Isaiah Nengo of Stony Brook University, affiliated Turkana Basin Institute, and De Anza College, USA, did the research. Senior author Fred Spoor of UCL in the UK and of the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany, was part of the research team. Humans are most closely related to living ape species including chimpanzees, gorillas, orangutans, and gibbons. Our common ancestor with chimpanzees lived in Africa 6 to 7 million years ago, and many spectacular fossil finds have revealed how humans evolved since then. In contrast, little is known about the evolution of the common ancestors of living apes and humans before 10 million years ago. So, relevant fossils being scarce and consisting mostly of isolated teeth and partial jawbones have left a real vacuum until now. It has therefore been difficult to find answers to two fundamental questions. Did the common ancestor of living apes and humans originate in Africa, and what did they look like? Now, these questions can be more fully addressed because the newly discovered ape fossil, nicknamed Alessi by its discoverers and known by its museum number KN-M-NP 59050, comes from a critical time period in the African past. In 2014, it was spotted by Kenyan fossil hunter John Ekusi in a 13 million year old rock layer and the Napudet area west of Lake Turkana in northern Kenya. And as I say, the fossil is the skull of an infant, but it is the most complete extinct ape skull known in the fossil record. Many of the most informative parts are preserved inside the fossil, and to make these visible, the team used an extremely sensitive form of 3D X-ray imaging at the synchrotron facility in Grenoble, France. We were able to reveal the brain cavity, the inner ears, and the unerupted adult teeth with their daily record of growth time, quote unquote, says Paul Tafaro of the European Synchrotron Radiation Facility. The quality of our images was so good that we could establish from the teeth that the infant was about 1 year and 4 months old when it died. The unerupted adult teeth inside the infant ape skull also indicate that the specimen belonged to a new species, Nyanzapithecus alesi. The species name comes from the Turkana word for ancestor, Ales. Until now, all Nyanzapithecus species were only known from teeth, and it was an open question whether or not they were even apes, notes John Flegel of Stony Brook University. Importantly, the cranium has fully developed bony ear tubes, an important feature linking it with living apes, adds Ellen Miller of Wake Forest University. Alesi's skull is about the size of a lemon, and with its notably small snout, it looks most like a baby gibbon. Quote, this gives the initial impression that it is an extinct gibbon, unquote, observes Chris Gilbert of Hunter College, New York. However, our analyses show that this appearance is not exclusively found in gibbons and evolved multiple times among extinct apes, monkeys, and their relatives, quote unquote. That the new species was certainly not gibbon-like in the way it behaved could be shown from the balance organ inside the inner ears. He went on to say that gibbons are well known for their fast and acrobatic behavior in trees, according to Fred Spoor, but the inner ears of Alesi show that it would have had a much more cautious way of moving around. Nyanzapithecus alesi was part of a group of primates that existed in Africa for over 10 million years, concludes lead author Isaiah Nengo. What the discovery of Alesi shows is that this group was close to the origin of living apes and humans, and that this origin was African. The remarkably complete skull was discovered in the Turkana Basin of northern Kenya 3 years ago, as the sun sank behind the Napudet Hills west of Lake Turkana. Primate paleontologist Isaiah Nengo of De Anza College in Cupertino, California, and his team started walking back to their jeep. Kenyan fossil hunter Johnny Kusi raced ahead to smoke a cigarette. Suddenly he began circling in place, and when Nengo caught up, he saw a dirt-clogged eye socket staring up at him. There's this skull just sticking out of the ground, Nengo recalls. It was incredible because we had been going up and down that path for weeks and never noticed it. The team carefully extracted the fossil from the rocky ground using small dental picks and brushes. Nengo knew immediately it was a primate skull, but that he wouldn't learn much more about it until he and his colleagues performed a more sophisticated analysis. At the Noel Gas Laboratory at Rutgers University in New Brunswick, New Jersey, researchers measured argon isotopes, which decay at a fixed, predictable rate within the fossil's rock layer, revealing that it was about 13 million years old. Back then, the dry, rocky landscape of today's Turkana Basin was a lush rainforest. Although the fossil looks a bit like a gibbon skull on first blush, Nengo says its dental pattern and teeth shape suggest its closest relatives are other Miocene fossil primates from the genus Nyanzapithecus, also found in Kenya. Yet its molars are much larger than those of the known Nyanzapithecines, indicating a new species. The researchers named it N. alesi, Nyanzapithecus alesi, or alesi for short, after the Turkana word for ancestor. Now, extremely sensitive X-ray imaging, which I already mentioned, performed at the European Synchrotron Radiation Facility in Grenoble, France, allowed the team to count the growth lines, so that we know that the alesi was about 1 year and 4 months, or 485 days old when it died. The X-rays revealed the presence of bony ear tubes in the skull, which acted as a balance organ, and the presence of these tubes, combined with the size and shape of the teeth, solidly mark Alesi, and by extension the other Nyanzapithecies, as apes. And all of this was reported in Nature, which is the British equivalent of the U.S. journal Science. The ear tubes present strong evidence that it is an evolutionary cousin to the ancestral line of apes from which humans and living apes derive. The new findings support an African origin for humans. Africa has been acting like a petri dish for millions of years, conducting experiments in evolution. Humans and our close ape relatives are just the latest evolutionary experiments to come out of that petri dish, according to those researchers in that article. And that brings us to a conclusion of this particular lecture. And there's still a lot of data to come in, because this is only the beginning or the very end of June. And by the time this book appears in August, I hope to have incorporated more of those field results. And of course, in coming years, as these volumes are updated, we'll keep you updated. So that brings us to a conclusion.